We're now going to look at another example where we're now mapping R2 to the polynomial's degree at most 1. And we're looking at the transformation that maps AB to 3A plus B plus A minus BX. The first thing we're going to do is show that it's linear. So I'm going to start with T, and now we're going to do C1, A1, B1 plus C2, A2, B2. And you can see that the constants that I'm using and within it allow me to use this linear transformation nicely as defined. So I used constants that weren't in the definition at all. And then I used A for A and B for B, and then used 1 as a subscript to denote the first point and 2 the subscript to denote the second point. This is often very helpful to use similar coefficients as how the expression was defined in order to prove linearity. And now I'm going to look at C1A T of A1 B1 plus C2 T of A2 B2. Here, this is going to equal T of C1A plus 1 plus C2B A2, comma C1A2 plus, or sorry, B2 plus C2 C second, C1 B1 plus C2 B2. I need to do this before I can apply my definition. So this is going to equal 3 bracket, middle bracket, C1 A1 plus C2 A2 plus C1 B1 plus C2 B2 plus, and now I have a bracket for C1 A1 plus C2 A2 minus C1 A1 B1 C2 plus C2 B2 all times X. And we're going to see that I'm going to have to increase the space as well as move this down. Okay, and what I'm going to do here is I'm just going to do some expanding using my polynomial rules, try and collect things a little bit better. So we're going to get C1 or 3 C1A1 plus 3 C2A2 plus 3 C1B1 plus 3 C2B2 plus C1A1X plus C1A2X minus C1B1X minus C2B2X. And to go from one step to the next all the way along, there's some justification we should be providing in terms of using our distributive properties and the definition of T all the way along. What rules in the vector space V did I apply? What rules in the vector space W did I apply? But I encourage you, work through it first and then input your justification after. And now here we're going to leave this as is, and we're now going to take a step and look at our right-hand side. So this is the left-hand side, and this is the right-hand side. Remember, we're trying to show that T of C1V1 plus C2V2 is equal to C1TV1 plus C2TV2 to prove it's a linear transformation. And now here, what we're going to do is we get C1 bracket 3a1 plus 3b1 plus, and it's big multiplying, a1 minus b1 times x plus, and now we have c2, and we get three a1 plus 3b1 plus a1 or a2, 3b2, a2 minus b2 times x. And now distributing, get 3c1a1 plus 3c1b1 plus c1a1x minus c1b1x plus 3c2a2 plus 3c2b2 plus c2a2x minus c2b2x. And rearranging, we can get 3c1a1 plus 3c2a2 plus 3c1b1 plus 3c2b2 plus c1a1x plus c2a2x plus, or minus, I should say, minus c1b1x minus c2b2x. And we can see that the right-hand side equals the left-hand side. So at this point, we can see that our right-hand side equals left-hand side. Therefore, T is a linear transformation. So we verified that it's a linear transformation. And yes, there are justifications that if we wanted to verify all the properties of being a linear transformation, it's good practice to go through and justify each of our steps. But you can see the process that would be involved to get there.